Hello, everybody. In the interest of starting spot on at 10 past, I'd like to start the introduction right now so that we can start exactly at 10 past. It's my absolute pleasure to welcome Professor Alex Gaeta to the campus. It's always a treat to have him come and talk to us. Professor Gaeta is the David M. Rickey Professor of Applied Physics and Applied Materials in Columbia University. He joined Columbia in 2015, where arguably, along with the team that he is part of, you can argue that applied physics has been transformed, particularly on the optical side. If you look at the activity, the amount of work, et cetera, before the team that he's part of joined, that was a very different scene. Right now, it's an extremely vibrant department and competes on a global scale. But before he was in Columbia, he was actually at Cornell University, where he was the Samuel Eckert Professor of Engineering at EE department and in the School of Applied and Engineering Physics. He actually did amazing work in that department, but he also, towards the end, ended up being the chair of that department right before he left onto Columbia. And Professor Gaeta, within the maybe past a couple of decades, he contributed over 300 extremely impactful journal papers in various fields. There are lots of world's firsts that Professor Gaeta actually has contributed to, and beyond the numbers and the citations and all that jazz, if you look at some of the world firsts, some of the insights that he at least personally sort of influenced me with the connections between applied physics and some parallels with engineering, it's extremely, extremely inspiring. But stop there. He actually founded arguably one of the most impactful journals in our field. People there are actually bona fide scientists that look at your papers. They're not sort of for hire. Not that I have anything against that, but it's not for profit journal, which is called Optica. And now it's franchised into Optica Quantum. So he's had an incredible impact on our field. And after being editor-in-chief, he didn't stop there. So he did academia, administration. He actually recently has started a company called Escape that he will talk to us a little bit about, hopefully. Just a little bit? Yeah, I think we should, just to inspire everybody. That deals with optical interconnects using comb sources, some of which, the ones that he will be talking to us about, and interesting architectures in disks, modulators and the such. Please join me in welcoming Professor Gaeta again.
Thank you, Amir, for a very generous introduction. It's always a pleasure to come here to Toronto. As I was telling some of the grad students, there's not too many places I know of that have a kind of extensive and broad range of photonics and optical physics as Toronto. So to be honest, I benefit a lot more coming from here than I think the other way around. So what I'm going to talk to you today is about work on over the years, we've done a lot of work on nonlinear photonic oscillators. I'm going to be talking to you about actual synchronization of nonlinear photonic oscillators. Most of you probably already know something about synchronization. What's really beautiful is that a lot of the things we're doing here can be done on a chip. And not only that, they can be done between different chips that are very widely separated. And then the best part of everything, of kind of almost everything that I've studied since I was a grad student, is I like working on systems that you can model really well. You can actually introduce theoretical models that are really consistent and can predict and not only guide you in terms of new physics and perhaps new technology in photonics. So just synchronization is actually a fairly old field. Huygens, now almost 3.5 centuries ago, did this grandfather clock, not grandfather clocks, but pendulum clocks that he hung on a wooden beam between two chairs. And what he found is, if these two clocks, I mean, back then you couldn't tune them so much, but what he found is that over a period of time, the two clocks would begin oscillating in unison. And he called it an odd kind of sympathy. So synchronization, you can think of as an odd kind of sympathy. So I'm not going to do this because it takes like 3 minutes to do, but I strongly encourage you to do that. There's a group in Japan that studies synchronization. extensively. And the reason why, as I'll show you, synchronization is it's something that occurs almost in every branch of nature or science, technology that you can think of. And again, that's what makes it, we're always looking for things that are universal, not very specific, but things that are universal. And synchronization is definitely one of those. And this is a case where they have this flexible board here. I don't know, a piece of plywood or something. And they get all these metronomes all together. And of course, even though you can adjust the metronomes, it's the discrete setting or whatever, they're never quite the same. And so they get them all started. And then I think in this case, it was 32 of them. And of course, they're all like random. But what you find over a period of time is a few of them begin actually oscillating exactly in time. And then it slowly grows and grows. And after about maybe 2 minutes, I think there's one straggler. I think it's this guy over here. But all the other 31 are going. And then eventually the straggler joins along. And I don't know why, but it always gives me this feeling of, it's a very dark feeling because, they all start in unison. So it has kind of a George Orwell feel if you see it. But anyway, I encourage you to go to this website. So it's a really great example. And I think that they've done it like, I don't know, with 128. So it turns out there's a universal model called the Kuromoto model, which shows up again and again and again for all these different systems. You could easily spend an entire talk talking about it. But one way of thinking about it, probably you often see it like in physics today or whatever, they talk about runners that are going around a circle and how to get them so that they're all running, in phase. And in this particular case, you have oscillators you can think of going around in a circle, that's theta. And so, of course, they all might have slightly different frequencies. And so, of course, if they're not coupled at all, they'll just continue going at the frequencies. They'll pass by one another, the faster one that's rotating a little faster, and so on. But if you put a little bit of coupling, in this case, it's a universal coupling, which is this sign here. And it turns out this does not work for cosine. So it has to do with, the derivative when the difference is 0 here. And so it just works with sine. But what you find for a certain number of oscillators, and of course, n could be the total number, it could be a very large number. And then you have some coupling coefficient here. And what you'll find if you do this is that there's kind of a certain frequency difference that is tolerated between all of them. And then there's a certain coupling strength. And there's a relation between how much tolerance you have in terms of this for a particular coupling in which all the oscillators can actually oscillate together and then become coupled, and then they stay coupled. Okay, so if you have sufficiently strong coupling or sufficiently narrow distribution of frequencies. Now, you might say, well, how do your photonic oscillators? They have nothing to do with this model. But as I'll show you later in the talk, what's amazing is that these complicated, what we call Kerr-Combe oscillators, which it's what's called Lujardal-Lefebvre model, which models, the dynamics inside of nonlinear. It's a very complicated equation, but what you can do is you can take that equation, reduce it, and if you do it just right, it actually completely is isomorphic to this Kuromoto model. So it just shows up again and again, and that's why it's used by much of this community. So there's two types of synchronization that typically occur. One is the one I kind of just told you, where you have coupling between all the components, and you could imagine in the case of photonics, you might even have lasers where you might have some type of coupling. The coupling could be evanescent, could be, actually a photonic waveguide that connects them. And they're all kind of interconnected. Of course, this is like nearest neighbor, and then you take this one that comes around all the way to here. So you can think about this kind of a circular thing where it's nearest neighbors. There's also a common one, which is also called force synchronization. And for those, who do this with lasers, it's called injection locking. Which, you have some master laser and you distribute a little bit of the light. And again, what makes it so powerful is you need just a really tiny fraction. I mean, we're talking 10 to the minus 8 of the total laser power is just injected in here, and it will determine the phase of all these is fixed to that. And so I'll call this typically the primary and secondary or auxiliary. I know this language has kind of been changed, but unfortunately I took this from a previous, from another plot. So that's one example. There have been other examples that have been studied in photonics, which is taking, different kinds of laser networks. And again, you have complicated systems in fibers where you have these fiber arrays and you have these microstructured fibers, photonic crystal type fibers, where you can get them all to go. There was a large DARPA program, which was to build sort of a, if I remember correctly, like 100 kilowatt laser where you use beam combining of all these different fiber lasers to get this. So these different types, and most of everything actually I'm going to talk to, of course, we're working on this part here, but most everything I'm going to talk about is kind of this force synchronization or injection locking. So everything that we study, uses this, what's called a microresonator, which you can think of as like the dog eating its tail type cavity. So we have a bus waveguide that comes in here. And again, think about this. This is a waveguide that's on a chip. So it could be a rib waveguide, it could be a ridge waveguide. But the fact is, it takes some light from the outside, which you couple in. It comes in here, and this waveguide is sufficiently close to this one that you have evanescent coupling here. So in terms of scale, this is not the scale from here, but this might be maybe of the order of 300 nanometers. And so some of the light leaks in here, comes all the way around, depending on the wavelength. If it's 2 pi coming around here, you'll have constructive interference to stay in here. And so, and if you're away from that, then you'll get destructive interference to stay inside, and it comes right out. And the scale here is typically of the order of 100 microns. Most of the microresonators we work with have Qs anywhere from 4 to 10 million, which is pretty good. I mean, there are other types of crystalline microresonators like whisper and gallery mode that can get higher. But the key part of the ones that we work with is that they're very tightly confining in the transverse direction. So they're maybe a micron squared or less. And so you have very tight confinement in that direction. And so that's why I call this kind of like a photonic atom, because there are certain energy levels, which are the modes of this microresonator. And then we're tightly confining the light, kind of like how the light's tightly confined in an atom. And again, what you can do is use this to greatly enhance the interaction. And so typically, if you come in with light that might be fairly weak, of the order of milliwatts, the light that's circulating inside here can be watts power. And again, that's why for nonlinear photonics, this is like, for me, the holy grail. When I was a graduate student, Bob Boyd always kept telling me, or telling the group, not just me, but all of us, listen, if nonlinear optics is ever going to be useful, it has to be down at the laser pointer level, milliwatts. And then you will start seeing applications of it. And up until now, the only thing that nonlinear optics has really seen, I would say, broad use, that is used by more than 10 million people or more than 1 million people, is the green laser pointer. And that's about it. And even that's going away. I no longer have a green laser. I used to be able to show that. This is my green laser pointer. There's like some beautiful frequency doubling going on here, but now they have a diode that works there. So no longer I can even say that. So I think the green diode laser market's collapsing. So right now, there's nothing that really broadly uses that. I should say that although these are the typical range that we work with, all these devices that we're working with are with Michal Lipson's group. This has been an enormous benefit because basically she makes the state-of-the-art devices, and so she has devices that can approach 100 million if we choose, but that requires a little bit more work, but certainly we can get up there. So the key part too is most of the devices I'll be talking about today are silicon nitride. And so these are the ones that are the fairly high Q. And we've had devices that can support 100 watts circulating. So you have 100 watts of power circulating in a 1 micron square diameter. So you can see how it's easy to do nonlinear optics under those conditions. So again, just a starting point, this is the nonlinear polarization. This is how it gets the name. This is not useful for explaining to my parents, but it is useful to explaining to you. Most textbooks stop here, but if you go to Boyd or any nonlinear optics textbook, they say, well, listen, it's a power series in the electric field. And so there's a lot of work going on right now. The rage is lithium niobate. And so that's the current material. It's kind of funny, if you actually look in nonlinear optics, there's been a tremendous amount of work over the years. When I was a student, and hopefully no one takes offense, but a lot of chemists that were working on nonlinear optics and showing these long benzene molecules that could have these huge optical nonlinearities, and they would say 10 to the 5, and it was just, I mean, a lot of funding went into that. And the problem is you could not make anything macroscopic. You couldn't make a waveguide out of it, or they were lossy. And so which are the materials currently right now that are the hottest? They're these old materials like lithium niobate. And the reason is because they can process them and make the losses extremely low, and they can make very high quality devices. So silicon nitride is currently, I consider, the best Chi3 material. So, and lithium niobate the best Chi2, and they're boring old materials, but they keep improving them. And so it's an important lesson on how these things work. So everything we're going to be working with is silicon nitride, so we're focusing on Chi3 effects. So let's see. So let's go back to this little picture. So now I bring in some light, and now I have a Chi3 interaction here. And so like the fundamental interaction you can think of with a single beam is that the index refraction of the material changes with intensity. Okay, so that's kind of interesting. What happens is now the light couples in here, and you can think of is that as I start increasing the power or tuning into resonance, what you'll find is the light will build up here, and the light will change its own index of refraction. But if it's changing its own index of refraction, then it's slightly changing the resonance condition. And so if it's changing the resonance condition, then that changes how much light is coupling into the cavity. So there's this very powerful feedback here, which can lead to a lot of interesting effects. And this is actually kind of a plot of what this looks like. So this is the intracavity power as a function of detuning. So if I just have the bare resonance, I have a Lorentzian line here. So it's just a single resonance. As I increase the power, just as I said, I start shifting at the peak. It starts shifting where the resonance is. It's no longer exactly at this part, but I've shifted it. Of course, in the wings, it's pretty much the same, but near the peak, it switches. And now let's say I increase to even higher powers. Well, you can actually get a regime where now I actually have 3 steady states that can exist. I have the one down here, this one here, this one here. And so this is called optical bistability. This is what I was obsessed with as a second-year graduate student and studied it a lot. People thought they were going to build optical computers based on this. But that's another story. And but what's interesting about it is normally what you can show is that this state is unstable. And so you can see the optical bistability. When I come in from this direction, when I come in, I keep tuning, I get to this point, I hop to here. And then if I keep tuning, I go down. If I go in the other direction, I keep tuning, I get up here, and then it drops down. So that's where you get the optical bistability. And the reason I point this out is because, we were always looking for systems to do this back in the 80s. There weren't any good systems. And now, we have these micro-resonators that can easily do all this. And in fact, much of the dynamics is caught up in how we generate many things. But it turns out it's not even so simple. These things, which I just told you, these are the steady states. These are not even stable themselves. And these can actually become unstable. And so probably the simplest version is when you tune on in here, you have what's called a modulational instability. And I'll talk about this more in a second. This is kind of the basis for the talk, these 2 instabilities here. But what will happen is under the right conditions and the right dispersion, you'll generate a signal in idler at this point here. And so now you can see I have a steady state here, and these weak little side modes comes in. So it's like a modulational instability. If I look in the time domain, it's like a modulation here. And so this optical parametric oscillator, if the gain exceeds the loss inside my microresonator, then what you'll find is that these can actually grow and be comparable in strength to the pump. So that's called an optical parametric oscillator. There's, of course, Chi2 versions. We're studying this Chi3 version. On the other hand, on this lower branch, what you find is when you go through here, what you'll find is you'll drop back down and tune here, and now the instability becomes even more complex, and you can actually generate what's called a comb oscillator or a microresonator comb. And here, what you find is under the suitable conditions, you can actually excite a pulse that circulates around the cavity. You take the Fourier transform of a pulse circulating and periodic in time. What I get is, a comb in the frequency domain where the spacing is how long it takes for the pulse. The spacing is 1 over the time it takes for the pulse to circulate around the microresonator. And then the total bandwidth depends on how short the pulse is. So these are the two oscillators that I'll be talking about for the remainder of the talk. One is an optical parametric oscillator. And for the most part, I'm going to focus on this comb oscillator. This has been, I would say, kind of maybe one of the real hot areas of research over the last 15 years or so. And there's been a lot of interesting work. And what's beautiful about this system, again, I'll reiterate, is it has a lot of interesting nonlinear dynamics, almost all the nonlinear dynamics you can think of. And at the same time, you can model it very well. And so it turns out to be a really beautiful system to study. So what I'll show is synchronization between different comb oscillators. And I'll take it even one step further, is to show that even different types of oscillators can actually be synchronized. So it's possible to synchronize this optical parametric oscillator to a comb oscillator. So these combs, this is the only part I'll tell you about, so I'll mention what Amer said at the very beginning. They have lots of different applications. And what you can think of, it's a frequency ruler. So the spacing of these combs, when it's truly what I call an optical frequency combs, or a lot of people call them combs, but those are only what I would say approximate combs. But a true comb is that these are pretty much discrete lines, and the spacing is identical across here. So if I measure the spacing here, let's say I measure 100 gigahertz, it's absolutely identical to 1 part in 10 to the 16 of the spacing over on this side. And so that's what makes it particularly useful, because once let's say I could line up one of these lines to some atomic reference, I then measure this is a microwave domain, I can make a measurement of that frequency difference. So then that means I know all the lines perfectly well. So it's my ruler. So in fact, if you look at what people are doing, there's astronomers putting them on telescopes to look at light that's coming. And what they do is they use that to make measurements of the spectrum immediately and compare it so that they can see, what chemical elements are coming from deep space. The ones that I focus on in the lab are for chemical biological sensing, which is that you can use this for many different kinds of spectroscopy. And there's a lot of beautiful spectroscopy that you can do with combs, dual comb spectroscopy, and so on. The one that Amir mentioned, we started a company based on using this for data communication, photonic interconnects for AI and high performance computing, because, getting, let's say, 16 lasers all operating at a fixed wavelength channel for a WDM, wavelength division multiplexing communication system, is non-trivial. It's very expensive, actually. But here, starting from a single pump laser, we can generate 16 lines easily, and it is a perfect grid. And so it turns out that is potentially very useful to datacom. So if I'm looking for the one, at least near future, potential high impact nonlinear photonics application, it is in this optical interconnects. We've also been working a lot on optical clockworks, so all optical clocks, and people have used a lot of different types of fiber lasers and so on to make the most accurate optical clocks. So if you look at current state-of-the-art Junyis, they're better than 10 to the minus 18 accuracy, and there's a optical frequency comb that's at the heart of that particular optical clock. And then the one I'll talk about here today is one that we just did recent work on, ultra low noise microwave generation, and it involves synchronization. So that's why it fits in really well here. So what's the whole basis for the nonlinear process? It's 4-wave mixing, just like it sounds. You have a Chi3 susceptibility. So I take E cubed. I take 3 waves that are all different frequencies. I cube them, and I'll get a 4th wave. Okay, and of course, maybe some of these are the same frequency, but the fact is you'll have a number of different processes. Here I just show one where I annihilate a red photon, a blue photon, and I generate an orange photon and a green photon. Okay, and it turns out that, just as I've shown here, you have energy conservation for this process to occur, so you're stuck with that. But the more subtle one is, does it occur efficiently? And then that means you also need momentum conservation. And so there you have a phase mismatch between the different propagation constants. And although you might say, well, these just differ from the omegas by C, but they also include the refractive index. And even though refractive indices may be just slightly different, it's enough to really upset and prevent you from getting this delta K to be 0. And so typically this is not so easy to get to be vanishing so that you can have this process occur efficiently. And so part of, one of the things my group has worked on for the last 20 years is precisely understanding and determining what are the conditions in which we have a chip and how to get this four-wave mixing to be very efficient and to achieve phase matching. So here I'm going to show one special case where now it's not 4 waves. I'm really going to count the pump wave twice, and I have a signal and idler. So I'm going to annihilate 2 of these pump photons to create a signal and idler photon. And so I have a waveguide. I'm going to pump it, and hopefully under suitable conditions, the signal and idler can actually grow or achieve what's called parametric gain. Okay. And the beauty of this is, unlike a laser where you're stuck with what nature gives you, the atom or molecules that make up the gain medium, here I can put the pump almost anywhere. So this parametric gain in fibers, in semiconductor media can, under suitable conditions, can occur anywhere from the blue to the mid-infrared. Okay, so we've done, covered this. All you need is a single pump laser, and then you can do forward mixing. But that's not all. Of course, you have to do the phase matching. And the phase matching typically for this process requires anomalous group velocity dispersion. So this is, I'll be coming back to this point a lot, but this is kind of the main theme takeaway, which is that you need anomalous group velocity dispersion, which typically is not the case. So if you look at glass, there's a point at which 1.27 microns where the group velocity dispersion above 1.27 microns becomes anomalous, below 1.27 microns becomes normal. And so, so this is why in optical fibers, if you look at all the four-wave mixing that has been done there, it was always above this kind of 1.3 micron range. But if you can do that, what you'll find is you get this very funny gain profile. So you have a pump, a signal and idler, and the gain actually increases roughly linearly. It peaks, and then it drops suddenly down here. And so this is what the gain profile looks like for this process here. And where it peaks is precisely where delta K equals 0. And you'd say, well, why isn't it where the, why do you need anomalous group velocity dispersion? Well, it's due to the fact that you have other processes like self and cross phase modulation, which I'm not going to go into. But the fact is the pump, it influences its own phase, and then it influences the signal and idler's phase twice as much. And so because of that difference, you need a little bit of anomalous group velocity dispersion to compensate. And at this point here where the gain peaks, it's 0. And so that's the whole key. So to build an oscillator, this is what, basically I think all scientists are, you have gain and you build an oscillator. That's the next thing you do. Okay. And so you start off with a single frequency pump. I have a cavity here. In this case, it's the part that provides feedback. So I pump it. If the gain exceeds the loss, what you'll find is you look at the output and you'll get strong signal and idler signals. And where they typically peak is precisely as I just described here. It's going to be roughly at this point where delta K equals 0. And this is what's called the optical parametric oscillator. So the first one that was done was actually Kerry Vahala's group at Caltech. He had these beautiful Whispering gallery modes where he took fused silica, took a CO2 laser, kind of melted it, and he could get these very, very high Q cavities. He would then bring a tapered fiber close to the edge of it and excite the mode inside this Whispering gallery mode, and he could see a signal in idler at this point here. And so that represented, kind of the first, I would say, in a microresonator based optical parametric oscillator. And then pretty much every platform that you can imagine has shown these type of optical parametric oscillators. So, obviously the early ones were silica, but then they also had Whispering gallery modes, in these fluorides and quartz. But again, these weren't terribly practical. You had to get a nanotaper fiber, so these weren't like robust. You had to put everything, you had to protect it from any air currents or anything else. And really the first ones that were done in planar geometry were actually done by us at Cornell with Michal, which was silicon nitride and in silicon. Okay, and then pretty much every platform now has shown these type of optical parametric oscillators. And as we'll see, it's the same group that has also produced these combs. So these combs are generated in all these different platforms, and so it can exist. And again, the beauty of everything I'm telling you about, it's universal. It doesn't correspond to a particular material system or anything. You just need it to be highly transparent. And if you have some nonlinearity, and in fact, I would say that almost you could argue. So let's pick silicon nitride, because I already said this is the best one. You say, well, why is silicon nitride the best one? The best should be aluminum gallium arsenide. Maybe Stuart would say that. And you have these other ones that are great. And what I'll say again is that the highest Qs that have been produced in these planar chip-based structures are still silicon nitride, up around, close to 100 million. But then there's a second subtle point. This is actually particularly important for quantum photonics, which I won't be talking about here, but a lot of the work that we do, it's a subtle point, but a very important one is there's no Raman, at least no observable Raman. So Tobias Kippenberg and I have had this standing argument for 10 years on this, but I'll just stand by this, that there is no Raman in these systems. There should be, but we don't observe it. And if it's there, it's very small. So I'll just say there is Raman, it's just really small. All the other materials are plagued by Raman. And so you always have competing effects with Raman in these other systems. And so that's why the silicon nitride turns out to be so good. So what, here's an example of, just a simple waveguide. It's typically, again, for silicon or silicon nitride or lithium niobate. These have fairly high refractive indices. And what does that lead to? Well, when people were first trying to do nonlinear photonics on a chip, this was the part that was they said is why it's going to revolutionize nonlinear photonics. It's because it's confined to a region less than a wavelength. So in other words, when you looked at 1.5 microns in silicon, the wavelength inside there is a fifth of 1.5. So it's actually about 500 nanometers. So these devices were absolutely tiny. The confinement was huge. This was about 300 nanometers squared. So you had incredibly tightly confined light, and they said that's why it's so important. But all the four-way mixing they never saw parametric gain, they never saw any of the large conversion efficiencies. And the key part there is the subtle point is it turns out the same thing that gives you the tight confinement allows you to engineer the dispersion. And I think in nonlinear optics, time and time again, what's proven is not so much the nonlinearity. It's an amplitude that you can, do nonlinear optics with very small amplitudes. It's the fact that you can engineer the dispersion. Because if you can engineer the dispersion, then over the entire length of your interaction, all the atoms are producing the nonlinear light, whatever light is being generated in phase. And so all those atoms are contributing. And that is the key part. And so I'll just, phase actually matters more than amplitude. And so it turns out, again, nature, it's one of the few times nature is kind, we're always fighting it. But here, the same part that gives us confinement allows us to engineer the dispersion. So here's what you can do. This is a silicon nitride microresonator, pretty simple one, nothing too exotic. So you turn up your power, you tune into resonance, you turn up your power, and at about 73 microwatts, you see threshold for gain. So we can do pretty nice nonlinear optics at the 100 microwatt level. And this is a solid state device. There's no resonance, there's no material resonance here. This is just, tuning into resonance, and you can, really beat Bob Boyd's threshold by a lot here. And so this was kind of, I think this is still the record for planar devices. So, but, what do you do when you generate power? You generate an optical parametric oscillator. You don't stop there. You keep turning up the power. And it turns out you do maybe some other things. You tune as you turn up the power. And sure enough, if you keep tuning, what you found is not only do you get parametric oscillation, you get this whole frequency cone that I told you about. And initially, what everyone said, and it took about almost 3 or 4 years for us to fight this, was that this is just cascaded four-wave mixing. So you might say, oh, yeah, these two frequencies get generated, and then they mix with a pump to generate the next one, then it mixes with that, but it's not so simple. In fact, this can actually, under suitable conditions, lead to a pulse that's circulating around here. And these lines have nothing to do with cascaded four-wave mixing. And that turns out to be very important because if you had any noise or anything, the noise would also cascade. So the noise at the edge of the comb would be, n times larger than the noise for the here. But what you find is it wasn't. When you get into this, what I call a mode-locked regime, where these are all have a certain fixed phase relationship, you're actually generating a pulse inside the cavity. And then the noise of all these lines is the same. And so it turns out that there's this beautiful model that was actually developed by primarily by Louis Lujato, and it was for transverse nonlinear optics in cavities. But it turns out you take instead of this being X, you replace it with a what's called a fast time, which is literally the time it takes to go around the cavity, and you have this nonlinear Schrodinger equation model. For those of you who've ever studied the House model for mode locking and lasers, it's identical to it almost. It has many of the same qualities. What are they? You have cavity loss and detuning, you have dispersion, you have this nonlinearity forward mixing, and for the case where you had a laser, mode lock laser, you would actually have a gain part as well, which would have a certain bandwidth. Here we have a CW pump, continuous wave pump, which is pumping it. So that's how it does it. But just like almost all the nonlinear Schrodinger equation systems that I know of, they allow for solutions, soliton solutions. So here are the solutions that are allowed. If you look at the field inside the cavity, you have a CW component that's related to what you put in. And then you can have actually N solitons that are existing inside this cavity. And again, like many of the soliton solutions, they're hyperbolic secants. And so these soliton solutions were known to exist in the spatial case, but when people started figuring out you could model this, use this to model microresonators, they said, they should exist in microresonators as well. And so what you find is that actually you could have these soliton solutions. And I'll talk a little bit more of these in a second. But I'm going to say something, and this is maybe controversial, maybe not so controversial, is actually I would say that the soliton solutions are just the ones that we can write down the solutions. But I would say there's maybe an infinite number of solutions that can exist in which the field can circulate around the cavity as a pulse. It may not be a beautiful hyperbolic secant pulse, but it's a pulse that actually can circulate around the cavity. And I would say that for a particular dispersion, under the right conditions, you can excite that pulse. It may not be a clean looking pulse, but it'll still lead to the same kind of mode locking that we're familiar with for soliton mode locking and so on. So that's why I say that there's both solutions, and I would say this is still an open question in the field, is what are the solutions beyond? And are those really solitons? Do we call them solitons? Or are they solitary waves? These are called cavity solitons, so they're kind of, or dissipative solitons, because there's loss within the cavity, but this is still an open question here. And I'll talk about this because much of the work that we do is looking at these non-soliton solutions because they actually have a number of advantages over the ones that are soliton solutions as well. So here I'll just show you an example. So typically the way people excite these microresonators, they have their silicon microresonator, they take their single frequency microresonator, and I'm not going to go through the details, but there are thermal effects that occur there along with nonlinear effect, and it really complicates things. And there is a little dance that you have to do to get into the regime where you excite the microresonator, where you actually have to tune fast enough, a little bit faster than the thermal nonlinearity, which is pretty fast. In these, it's 10 microseconds. It's the thermal response time because these are very small cavities. And so you have to do a little dance with your laser in order to get into this regime. We have taken an opposite approach, which I think maybe I was surprised more groups didn't adopt it sooner, but they're starting to, which is you keep your laser fixed, and now you put a little piece of titanium on top or platinum on top of this as a heater, and you heat up the comb this way. And this allows you to actually control the cavity mode with respect to the pump. You can tune this very fast, also on the order of microseconds. And so this allows you to kind of get into the particular regime you want. You can program it with an AWG, and it's very easy to get into the soliton regime. So this is what it looks like. So we have a bus waveguide here. We couple into the microresonator, and then we look at the light coming out. And so here is just kind of looking on a slow time scale at the transmission as we tune this resistive heater here and heat it up. So you can see it's pretty fast time. We're tuning in fairly quickly. So I'm tuning into resonance. So initially the pump starts going down. Then you see there's a lot of noise here. And actually, if you could look at this, which we have, this is actually chaotic. So this is like everything I did as a second-year grad student. It's just amazing that so many years later, I'm doing the same thing. But what's interesting is then all of a sudden you get out of this regime, and then all of a sudden you get onto what are called, and this was first described by Tobias Kippenberg's group, which are these soliton steps. And what you find is this corresponds to soliton solutions where there's 4 solitons circulating around, 2, 1, and then you get out of resonance. So this is doing a little dance through the resonance here. And again, it has to be done on a very tight time scale. So in principle, what you could do is stop at a certain point so that you could actually see the 4 solitons, or stop here or stop there and see it. In fact, when you do this experiment, so first of all, here are the spectra. So this is the case where there's a single soliton circulating around. This is the pump wave sitting up here. And what you see is this blue dotted is a hyperbolic secant squared. So as I told you, you can model this really well. And it's almost perfectly aligned there. And this corresponds to a case where the spacing here of this comb is precisely equal to roughly the free spectral range of your microresonator. But as I said, you could stop at the 2 soliton step. And now it turns out the solitons are not just 2 solitons, but they're exactly opposite one another. And so in this particular case, every other line is missing because now the rate is increased by a factor of 2, so the spacing is there. And of course, the 4 soliton is the same. And again, it turns out that they space themselves equally so that 3 of every 4 lines are missing. And so you can see, just like I showed in the dynamics here, and you can do the experiment and model it very well. So here's an extreme where you now get to the case where the comb spans an octave. If you've ever generated a frequency comb and you give a talk on it, the first question everyone asks is, well, can you generate an octave? And the reason is because if you can generate an octave, then you can what's called self-reference the comb, which is your frequency double the red side, and you compare it, for example, with the blue side, and it turns out that allows you to extract what's called the carrier envelope phase of the comb. So I'm not going to go into that. But here's an example where starting with just 2 milliwatts of power, single line here, I can generate 126 terahertz of bandwidth. This comb is perfectly spaced here. So, you know, it's extreme nonlinear optics. I used to did a lot of work in ultrafast with, you know, ultra intense beams, gigawatt peak powers, and that is called extreme nonlinear optics. To me, this is extreme nonlinear optics. I'm generating thousands of lines at 2 milliwatts, starting just from a single frequency. So in the normal group velocity dispersion regime, you said, well, hey, you just said that you cannot generate pulses in that regime. But it turns out there's always, how should I put it? There's always defects in some sense inside the cavity that change the dispersion. What are the defects? It could be coupling to a higher order mode. If you have a higher order mode where its mode is close to the one that you're exciting, then you'll get an avoided mode crossing. That avoided mode crossing will change the dispersion slightly so that now you can't say I'm strictly in the normal group velocity dispersion regime. And they've had lots of names here. Okay, I don't know if any, I know this one is wrong. Okay, so I know him also. But they're not dark solitons. But certainly there are dark pulses, platicons, switching waves. These are part of the story, but not the full story. And so I'll just say that you can get mode lock comb generation in a normal GVD regime. And I would just say, this is just a general thing, this might even be controversial, is that mode lock combs are just a general feature here. And what you find is that they don't have to be hyperbolic secant. In fact, hyperbolic secant ones are just a very special case. Now, what do I mean? So here's an example. This was actually this was only within like less than 2 years after we first discovered them. We got these spectra that we looked at, which look like a comb. But if you actually look at the RF spectrum, they were very noisy. So these are what I called not very good combs. And certainly people who are doing precise measurement would say that these are not combs because they don't have a low RF noise. And what that means is that these are jittering with respect to each other. But what you found is that, you would tune it a little bit. And what we found is we would get these quiet regions where the comb pretty much looks like here, but this would have no RF noise, and you could check it out to 10 gigahertz. And in fact, what we would do is measure what are called eye diagrams. These are used in data communications, which are used to look at your ones and zeros. And what you'd see is here it's really dirty because there's a lot of noise there. That's dirty. But when you get into this, what I call mode lock state, you would have perfect eye diagrams indicating that, and we could check each of the lines here, and they were all identical in terms of their performance. So this was hinting already, and we say in the paper, this suggests that these are mode locked. Even though this doesn't look like a hyperbolic secant, doesn't look like anything. Probably for these combs, we were exciting a higher order mode. We were right close to that point, and there was a mode coupling there, which was generating the comb and allowing you to mode lock. And of course, one of the motivations, as I said earlier, is that you could take each of the lines from the comb, and what you found is basically the performance of all the lines was identical to what you started off with a single laser. So if you had a good single laser that had a megahertz line width, all the line with the combs. And again, there's been a tremendous amount of research. The original paper was done here showing that all these comb lines could behave really well, as good as any of the lines here. And so this is one of the big pushes that as Amir mentioned, the company we founded recently is based on that, but there are a number of companies that are looking at this. So here's kind of what I would call a real, fancy, all bells and whistle, normal GVD comb. Okay, and there's a lot of little innovation here, which I'm not going to go into, but I'll just tell you. You start off with a pump laser, you come in and excite it, and you have a primary part here. And you'd say, well, why do you need the secondary one? Well, it turns out if you take the secondary and you can thermally tune them separately, but you make it so the mode of the secondary line is close to that of the pump laser and close to this one here, what you'll find is that you will actually get an avoided mode crossing. We'll have mode coupling. In other words, I have one possible mode here. I have another one where it could go through this way. And so those are two different, modes there. They interfere and you get an avoided mode coupling. But sure enough, what you find is you actually can get a full mode lock soliton comb. And so you can tune them. And the beauty of this, I won't go into it, is that it's very deterministic. The soliton combs are a little bit problematic. These are really deterministic, very easy to generate combs in this way. And so here's what the original one, we showed that you measure the coherence, that's the red here. When you were mode locked, very high coherence. If you were not mode locked, the two combs look the same pretty much. But here you can see it's a low coherence comb. Here it's a high coherence comb, and this is this mode locking that occurs. I won't go too much into details. But you can do the modeling here. You can see here that what we're doing, this is now looking at this dispersion. So the fact that it's this parabola here, this indicates that it's normal group velocity dispersion, but you see it's distorted. And these distortions are due to the fact of these repeated mode crossings because the two of these are not absolutely identical, the auxiliary and the main. And so you get these avoided mode crossings. And you see how it distorts the dispersion at that point. And you can use that to actually generate the comb. And it looks just like modulational instability, even though we're in the normal group velocity dispersion regime. And this is the theory. And just like soliton combs, you can generate pulse here, 1 pulse, 2 pulses, 3 pulses circulating the cavity. So these funny combs, the combs don't look beautiful, but they exhibit all the same behavior as the soliton combs. And you can see you can get pretty broad spectra here. And note that these are not hyperbolic secants. They look very complicated. They have these little wings. They have wiggles everywhere. But, these are, for all intents and purposes, mode locked. And so here are the type of combs. And again, the beauty of this, we can do this experimentally. And so you can see you can excite the comb here with 1 FSR spacing, 2 FSR, 3 FSR. So this indicates there's 1 pulse circulating, 2 pulses, 3. The key part where you can see here why these combs are so attractive is note how flat they are. They also have over 0.5 milliwatt per line. So these have a lot of power in them, which there's not too many comb systems that can produce this kind of relatively high power and be so flat. So 75 lines above half a milliwatt. And also there's another key part, very high pump to comb conversion. The solid time combs are a few percent. So these combs are up around 40%. Okay, so sorry, we finally just got to the synchronization part, and I only have a few minutes left here. Oh, I still have 15 minutes left, right? Okay. So here's, so now what we're going to do is take these nonlinear photonic devices and synchronize them. And so you can imagine, we can take two different combs, pump them even with the same pump, and you'd say, well, with nanofabrication, you can make these ultra precise. The two combs coming out should be identical. But of course, there's inherently fabrication uncertainty. You can never make these identical. They'll always be off by a little bit. And it's almost fundamental. In fact, just the height of the waveguide, if you look at the dispersion, which I tried to emphasize here, if the height of the waveguide, which is that you're talking about, is 1 nanometer different, that will lead to a 1 nanometer shift in the group velocity dispersion to 0 point. So if I'm shifting the zero group velocity dispersion point by 1 nanometer, that shifts the dispersion so that they're just slightly different. So there's no way you can ever get these the same. Fabrication thicknesses, you just cannot guarantee across a wafer even 1 nanometer uniformity across the wafer. So it's really fundamental. There's also the fact that if these are slightly different temperatures, materials like silicon nitride, the index of refraction depends on temperature slightly, but it's enough to make these no longer identical. But what you can do is take a tiny amount, and by a tiny amount, less than 1%, and I just take a little bit of the light coming out of here, and I feed it into the light over here, and just like injection locking a laser, you can get these now to be identical. And what's interesting about this is we've done this with distances that are now 20 meters. So we actually have, there are two different chips in the lab, 20-meter fiber separating them. So these are about 100 micron in size. We mode lock both of them. So there's two little pulses here that are about, I don't know, sub-picosecond pulses circulating around the cavity and they go around at 100 gigahertz. And you can get them both so that they actually are perfectly in sync with one another. So the two pulses are both circulating exactly the same, even despite this large distance being across. So I won't go too much into details, but okay. So the reason I show this is not to show the actual details, but you now have these two combs, and you can model, Luciano-Lefebvre model. So it's getting pretty complicated. We've actually done this with up to 100, but here I'm just showing the case of two, and it's really complicated. And the key part is there's this mismatch here between the two because they're not identical. But, I had a fantastic postdoc, Jay Yang, who is very theoretically strong, and he was able to take these equations and reduce it to this. And it turned out that if you look at the position in time of the two solitons, let's say it's actually one with respect to another. So you can think about the time difference between the two solitons. Well, they have a natural drift race. They have a coupling, which is related to that photonic coupling here. And it turns out that it obeys this sign of the difference here. So this is isomorphic to the Kuromoto model. So everything that anyone has ever seen in the Kuromoto model can occur in this system here. And so it's really, I think, a tour de force to show this, that really the same kind of behavior. And sure enough, so we do the experiment where we take this one CW pump here. We take a little bit of light, and in this case, we've done it with up to 20 meters. We couple a little bit of that light here, and then we study a number of the different properties, and we compare the two combs, and we look at the spectrum, the RF spectrum difference, and so on. And so here is where you're actually measuring the frequency difference between the combs. So if you actually beat them together, in general, let's say they're pretty close, but let's say they're off by 10 megahertz. So let's say the pump will be identical, and then the next comb line is, let's say, 100 gigahertz. The other one will be 100 gigahertz plus 10 megahertz. So when you beat them together, you'll get actually in the RF domain a 10 megahertz signal, which is the beating between those two. Then I'll get a the next line, which will be off by 20 megahertz and 30 megahertz. So actually, when you look in the RF domain, you actually see a comb too, which represents the difference. And so here is where we're measuring that RF beat note. And what you find is we can tune the heater of 1, which is effectively tuning its free spectral range or the comb spacing ever so slightly. So if we do it in red, what we do is, we see that there's a frequency difference that actually goes through 0, and then it keeps going. Now, of course, plus and minus is the same, so it goes up this way. But for the case in which we now couple small amount of light, 0.5%, what you find is it undergoes a phase transition and just stays down at 0. They stay, and then if the difference becomes too big, it then hops back up. So that's kind of the first indicator there. And then you can measure that. And what you measure is how much light do I need to transmit and how much tolerance in terms of frequency difference is allowed. So for example, for a case of 0.2% of transmission, what you find is I can tolerate this much difference. If that difference is larger, then the two combs won't sync. Okay, and so the blue dots here represent the experiment. And again, just to show how beautiful the theory is in terms of closely modeling, this is the solid line represents results from Lujado-Lefebvre, and you can see you get really good agreement between the two. And so then you can take this, and of course, everything I've told you about is when they're very close to each other, but then you could imagine doing with harmonic or subharmonic. In the case of subharmonic, for example, you would have the comb line difference, which is bigger here, and then you'd have one which is much smaller, but they differ. The ratio is an integer. And then you could do the other way around, where the comb spacing here is much tighter, and then this is larger by a harmonic amount. And then you could even imagine having the case where it's an integer ratio between the two. And again, you do the experiment, you see what is this difference here. Oh, and I should have said that this synchronization regime is also in synchronization. It's called an Arnold tongue, because it looks a little bit like a tongue in this particular case. And so what you can see is for harmonic synchronization, 3-to-1, 2-to-1, we get very good agreement. We have the synchronization, we can do the ratios, and then we can also do subharmonic as well. And so I'll tell you, I'm going to finish up, this is 1-to-2, 1-to-3, but now I'll tell you an example where we do 1 to like 500. And I should say, before I go on, you can also do this with normal dispersion combs. I'm going to hop quickly, but just to show it's not unique to soliton combs, you can take 2 combs and you get all the same behavior. You get Arnold tongues here, and you can synchronize ones that are very different. You could imagine doing coherent beam combining, where you have all these normal group velocity dispersions. You want to, on the same chip, you want to get a more powerful comb. This is one way of doing that. And here, for example, is a device that combines 2 on a chip. So you have 2 comb generators here. You have a little coupling link here. You have heating parts that control everything. And you can actually get this whole system synchronized here. And you basically can increase the comb, ideally it would be 3 dB, but we can increase the amount of power in the comb by almost 3 dB in this case, very close to what we expect. So the last part I'm going to finish up with is how you can generate ultra-low noise microwaves using synchronization. So here's a case. So how do you generate microwaves? So very early on, the very simplest way of doing it is you take 2 lasers and you beat it on a photodiode. And then you can tune the lasers that adjust the microwave. So that's very simple. It's also very noisy. You'd say, really? Why? Why should it be so noisy? And it's really noisy because it turns out that if you look at the line width of 2 lasers, they obey what's called a Charlotte-Towns line width. It's a Lorentzian. And there's a limit to that. But it's a Lorentzian function. And Lorentzian functions decay very slowly. And so if you actually look at the microwave signal that's generated from beating these 2 together, it turns out that it's actually fairly noisy, and it can't compete with, let's say, sapphire or quartz oscillators, which are kind of maybe more the commercial state of the art. Now, you could, but then you have to make the line width sub-hertz. This is not something you could take to the field. To build a sub-hertz laser, that's something you have to build in the lab, stabilize everything. Not so easy to do to build sub-hertz lasers. I mean, I think the record is like 10 millihertz is the current record for line width of lasers. But even that 10 millihertz could not compete with like some of the sapphire and quartz oscillators. And so this has been kind of this. But it turns out with the development of frequency combs roughly 2 decades ago, this opened up a process by which you could actually generate ultra-low noise microwaves using photonics. And the way it works is follows. You take your 2 optical references, and instead of making this microwave, you make it much larger, maybe terahertz, tens of terahertz. And then what you do is you take this line and you beat it together with one of the lines of the comb here, and you lock it there. And then you take this line and you lock it here. And it turns out when you do that locking, the comb and everything in between gets locked as well, because there's a coherent comb. So by locking this comb to this line, this one to this line, I've now taken my signal, which was, let's say, 10 terahertz, and I'm dividing it by m, where m is the number of lines here. So if you take like a 10 terahertz comb, and let's say you have 1,000 lines, I now have a 10 gigahertz signal. You say, okay, so that's called optical frequency division. I've divided the frequency. But in dividing that frequency, if you can think of that's everything in the exponential, if there's any noise in the phase, you also divide down the noise. And so it turns out that when you go through all the math, the phase noise and the noise power is actually divided by m squared. So you can divide the noise, let's say if you have 1,000 comb lines, you can divide that, that's 30 dB. That's 60 dB that you can actually divide the noise by. And so now I can actually generate microwave signals that are way below what the current state of the art is, let's say quartz or sapphire. And so this is the path to generating, and the lowest noise microwaves to date have been generated through this optical frequency division. And there's a number of many groups working on this. So in work that we just published, now the key part though, when you look at this, is you need 2 lasers, and these have to be extremely high performing lasers, and I needed probably a laser to pump my comb source. So effectively you need 3 lasers. So if I go through here, we came up with a scheme which only requires a single laser. And it leads to the lowest noise microwaves you can, well, there were 3 papers that all came out, all slightly, proposing different approaches, but this is at least done on a chip. And so how do we do it? We take a pump laser, and one of them is used to pump an OPO. So it's producing a signal in idler. And we make that separation, let's say 10 terahertz. We then take the other one and we generate a soliton comb here. And then what we do is we take a little bit of light from the OPO and we synchronize it to this part here. And so now this is automatically doing optical frequency division without any electronic locking. We just use synchronization to lock the comb here to the signal here. And it does the optical frequency division all on the chip in a very simple device. This is 1 millimeter squared. So typically these devices take, optical frequency division is like half an optical table. And the beauty of it, there's no electronics. It's just done automatically. And so this is what we carried out. So you can think of the 2 microresonators could actually be identical. One of them is operating in the OPO region. We tune it. The other one is operating in the soliton comb region. So this is what the soliton is doing. This is what the OPO is doing. And if you want to think about it, it's hard to see here, but the OPO is just oscillating, right? It's just oscillating signal and idler. They just beat together to give you a sinusoidal signal. Note that the soliton is coupled right to the peak there. And what you can think of is that there's a little index change which kind of focuses the soliton and keeps it coupled to that point. So that's one way of thinking about how the synchronization is occurring in the time domain. So what you do is you have the soliton, which is drifting. You then start the coupling, and it couples right to the beating here of this OPO. And so at least theoretically, that's how you can understand it. And you can think of it, this is like subharmonic synchronization, but like a factor of 500 in this particular case. Now you'd say, oh, that's great. Yep. Oh, okay, sorry. Let me just finish up. Sorry, didn't know that. So I'll just get to the end result. So here's just an example of the signal. We couple here OPO to the soliton, and we've been able to generate, in this case, 31 dB noise reduction. In this case, and then we went to the extreme, which is to go to 16 gigahertz, and we see 54 dB optical frequency division. So I'll just finish up here. Just want to acknowledge a great group of students and postdocs who have worked on all this, and everything is done in close collaboration with the Ellipsis group. Thanks for your attention.